All right, so today we're talking about nuclear decay, everybody. And with nuclear decay, we first need to talk about nuclear stability. So with nuclear stability, elements prefer to have a one-to-one ratio of protons to neutrons. And we kind of talked about this earlier with this line of stability right here. And the further we get from that line, the more unstable an atom will be. So ratios that are further from 1 to 1, like 1 to 1.5, can lead to instability. And basically, that's when an atom's nucleus is not stable and it's going to eject, it's going to release, it's going to get rid of some particles to establish a more stable ratio. The number and the pattern is unique for each isotope. So again, here's our band of stability. And the further we get to this 1 and 1, the more likely we're going to have some nuclear decay, some radiation. So radiation, we have a little bit of vocab. A radioisotope is basically any atom, any isotope that has a poor proton to neutron ratio. So that means it's something that is unstable, something that will undergo nuclear radiation. Another word for that is nuclear decay. It's the loss of subatomic particles to form newer, lighter elements that have better ratios. Okay, and this can be done in a few different ways, and we'll talk about fission and fusion later on, but today we're going to be focusing on these three main ones, which is alpha, beta, and gamma. But before we go into that, I would like you to watch a little bit of video, just actually the first 5 minutes of this video. The link is right here. Go ahead and pull this open, and you're going to be taking notes. Remember, this unit, we're kind of practicing taking notes from YouTube videos. I'm sorry, this is a nuclear stability. You've already done that. It's this one right here. We're practicing taking notes, and the best way to take notes is using that pause button a whole bunch and the closed captioning, okay? I would say that actually the most important information from this video is between minute 128, so right there, and minute 4. All right, so you do not need to go beyond minute 5. So go ahead and take notes, and yeah, we'll meet back together in just a second. All right, everybody, so this is like the main takeaways that I wanted you to get from this video. First, that nuclear radiation is basically when subatomic particles, it sounds kind of fancy, but subatomic particles are like electrons, protons, neutrons, photons, things that are smaller than an atom. All right, it's what an atom is made out of. It's when subatomic particles are emitted, ejected, shot out of a nucleus. All right, and this video talks about 4 different types. We talked about alpha, which shoots out an alpha particle, and an alpha particle is essentially 2 protons and 2 neutrons. A beta particle is essentially an electron, but it has an interesting effect on the nucleus, and we'll look at that. Gamma, and that's basically high energy photons leaving the nucleus, but doesn't affect the mass number and or the atomic number. And neutron is basically just shooting off a neutron. Okay, so when I'm doing these kind of Cornell notes, I like to write a question right here that is answered over here. So what is nuclear radiation? Oh, it's this right here. What are their different types? Bam. And then my summary is basically that unstable isotopes will undergo nuclear radiation to become more stable. Radiation is when these particles are released from the nucleus. There are 4 types: alpha, beta, gamma, neutron. Each one emits a different thing and has a different level of danger. Like some of these are totally fine and some of these are pretty dangerous. Cool, cool. So what we're talking about here is alpha particles at the beginning, okay? So an alpha particle, and we use these Greek letters, all right? So alpha is kind of like a lowercase a, but it has a little bit of a little top hat. And if you want to, right up above, you can take these letters right here and copy and paste them. So if I take this alpha right here, I can paste it in this right here, okay? So the first one is alpha radiation. And basically it's a helium nucleus. So we can write this in right here. It's a helium nucleus. So it's basically 2 protons and 2 neutrons, okay? And that's kind of like the symbol for it, okay? But it's just the nucleus. There's no electrons included. And it's pretty safe. Like it's actually like not that dangerous. Doesn't really affect life that much. But here's the thing. Let's really talk about these equations because that's really how these things start to make sense. So this right here, all right, is our parent isotope. It's what is unstable, and it needs to become more stable. So what's going to do, it's going to emit. So the arrow kind of means emit or undergoes. And it turns into this right here, this 4,2, that's the alpha radiation, the alpha particle. And then it turns into this. So basically this atom turned into this atom by shooting off an alpha. But let's look at this. I have 210 on top here and 206 over here and 4 here. So this 210 minus 4 equals 206. 84 minus 2 equals 82. Okay, so there's still a law of conservation of mass. The number of protons that we started with and the number of protons that we ended with are the same. That didn't change. What changed here is the element. Okay, so what changed about this is that we had minus 4 to atomic mass and minus 2 to atomic number. Okay, when an alpha particle is shot off, it minus 4s to the mass, 210 to 206, and minus 2 to the atomic number. So the next type we talk about are beta particles, and beta particles consist of a single electron. Okay, the symbol that we use is this B right here. So I'm going to copy this and paste it down here. And basically, the effect that it has is it adds 1 to the atomic number. So look at this. It starts at 131, ends at 131. The atomic mass doesn't change. But look at this, 53, and it goes to 54. Okay? So it's plus 1 to the atomic number on the bottom. Okay? That's the symbol that we use. It's just a single electron, no nucleus. And the more energy that these bad boys have, the more dangerous they become. And the last type that we're talking about is gamma. And gamma is, it actually is just high energy light. It's a photon, okay? A high energy photon. And the Greek symbol that we use for it, maybe Latin symbol, is this one right here. It's kind of like a backwards lowercase y. That's what it reminds me of. And look at this. It doesn't affect the atomic mass. It doesn't affect the atomic number. All right. It's just energy. And it can be pretty dangerous energy. Okay. And like in comic books and superhero movies, this is the stuff that causes like radiation, like DNA changes that make you turn into the Hulk or whatever. So what I'm going to put here is no change to atomic mass or atomic number. So now what I want you to do is to practice this a little bit. Here are some different examples. They're a little blurry, but I think you can do it. So what I want you to do is just kind of analyze these on your own for a little bit. So here you have to kind of say, what is this? And you have to write it in the correct format. So I'll kind of help you on the first one. This first one right here is the parent nucleus. And it's called parent and daughter, like radioisotope. And why is it daughter, not son? I have no idea. But basically, it starts as uranium-238. And then what are the products? Well, it's an alpha particle and thorium-234. What kind of change, blah, blah, blah. So I want you to work on this page right now on your own. I'm going to go back to the other page so you can finish taking notes if you haven't. But once you're done, I want you to be working on this page right here. So the products here is that alpha particle right here, the alpha particle, and thorium-234, thorium-234. So basically this unstable radioisotope, aka parent isotope, turned into an alpha particle and thorium-234. What is an alpha particle made of? It's made out of a helium nucleus. And how did the atom change as it went through alpha decay? It had -4 to atomic mass. In other words, 238 to 234, and -2 to the atomic number. All right, how is the parent isotope different from the daughter isotope? Well, basically what I just said, but less protons and neutrons. So the next one we have right here is kind of weird, but I'm gonna help you interpret it. So let's look at this, what it starts off as. So what is this? Well, it's just a neutron. And how do I know that? One, you see the N, all right? But also you have a 1 up above in the atomic mass and nothing down here. So the only thing it can be is a neutron. But let's see what happens here when a beta particle is released from it. Okay, it's basically this beta particle is released, and now this neutron has turned into a proton. Okay, and low key, we don't need to know this anti-neutrino. Don't worry about that. It doesn't really affect us right now. What is a beta particle made of? It's made of a single electron. Okay, but what actually happens is that when this beta particle is released, a neutron turns into a proton. Isn't that crazy? And that right there will help gain that 1-to-1 ratio, or help it a little bit, because we'll have more protons and the same amount of neutrons in that ratio. And then in this last one, this is kind of just shows you that these happen in series, kind of like what I just described, is that we have, if we start with thorium-234, it emits a beta, and then it also has some, I don't know, some Pa-234, all right? How do the masses compare? Like, look at this, 234 and 234, they didn't change, okay, after a gamma radiation. So there's no change. But also, there's no change to the atomic number as well. So what basically happens here is there's no change in this, it's just lots of energy. No change in atomic number or mass, just loss of energy. Okay, and that's important. And again, these things happen like kind of together. So it's like this might happen, then to get rid of that electron, that might happen. And then while that's happening, gamma might be coming out. It's not like just sometimes one, it's like all this is happening at once, and sometimes very quickly, sometimes simultaneously. Sounds good. So I'll let you all finish these notes right here. And tomorrow we're going to be practicing these equations more, but I'll let you finish up the notes right now.